grade 12 learners. Welcome to today's physical science lesson. My name is Thabo Mboweni. This lesson is brought to you by the Northern Cape Department of Education in collaboration with Pagama Research and Development. Today's lesson is under the knowledge area, matter and materials. The subtopic is optical phenomena and properties of material. We are under the topic photoelectric effect. Now, let's look into the examination guideline. This topic is found in page 14 of the examination guideline, and in the CAPS document is found in page 132 to 133. We are under the knowledge area, matter and materials, with a total of 15 marks of your paper 1 exam. Let's look at the terminology that is very, very important for this topic. The terminology that is very important that you need to be aware of, we are going to start with the dual nature. The dual nature of light, it means a double nature. So in the double nature of light, you need to know that light behaves like waves in propagation and also like particles when interacting with matter. So that is what we call the dual nature of light. It behaves as a wave and also as a particle when it interacts with matter. The photoelectric effect, which is the topic for today, is defined as the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident or shines on the surface. So the light has to be incident or shining on the surface, and then we are going to get electrons ejected if the light is of a suitable frequency. The definition is very, very important. You will get 2 marks for that. The threshold frequency is also one of the most important terminology for this topic, which is the minimum frequency of light needed to emit electrons. There's a minimum frequency needed to emit electrons from a certain metal surface. All these electrons are emitted from a metal surface. Then we go to the work function. The work function is the minimum energy that an electron in a metal needs to be emitted from the metal surface. Now, the photoelectric effect equation that we are going to look at as we go on with the topic is E is equals to WO plus K max, where E is the energy of the photon or the energy of the incident light. We also have WO, which is the work function that was defined here. And then we have the K max, which is the maximum kinetic energy of the photoelectrons. You will understand all these terms as we carry on with the lesson. This formula can also be written in another way. That is another way of writing that formula. This is the energy of the photon. This is the formula for the work function. And this is the formula for the maximum kinetic energy. The spectrum, a band of colors with different wavelengths observed when light is dispersed by a prism. We are going to see this prism dispersing light as we go on with the lesson. The rainbow is an example of a continuous spectrum. So we need to be able to define the spectrum as a band of colors with different wavelengths observed when light is dispersed by a prism. The absorption spectrum is also very important for this topic. We are going to see it in the next lesson. It is formed when certain frequencies of electromagnetic radiation passes through a medium. That medium could be example of a cold gas, and then we get certain frequencies that are absorbed. So when certain frequencies of electromagnetic radiation passes through a cold gas, we'll get certain frequencies that are absorbed. And in that case, the absorption spectrum is formed. The atomic emission spectrum is formed when certain frequencies again of electromagnetic radiation are emitted due to atoms electron making transition from the high energy state to a lower energy state. So those are the definitions or the terminology that is very, very important and critical for this lesson. The baseline activity. At the end of this lesson, you should be able to answer this type of questions. Let's go through the question together and see what kind of questions we are expecting at the end of this lesson. Let's read the work function of potassium. We have talked about the work function in the terminology, which is the minimum energy needed to eject electrons from a metal surface. So here we see that the work function of potassium is 3,2 times 10 to the power negative 19 joules. And electromagnetic radiation struck a surface of this metal produces a photoelectric effect. The maximum kinetic energy of the photoelectrons ejected. Now we are being told that the maximum kinetic energy of the photoelectrons ejected is 4,20 times 10 to the power negative 19 joules. Now we are expecting questions such as define work function, which we have defined earlier as the minimum energy needed to eject an electron from a metal surface. We are expecting questions such as define the photoelectric effect, which is the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on that surface. So we are also expecting questions such as calculate the frequency of incident radiation, calculate the wavelength of incident radiation. At the end of this lesson, you will be able to answer these questions. Now, here's a solution to those two questions earlier. We write the photoelectric effect equation copied from the data sheet provided in the question paper. Then we substitute Planck's constant, which is also given on the data sheet as h, the value of h, and then the work function was given and the kinetic energy was given. Therefore, we only do the manipulation and then we get the answer. Then the next question was the wavelength. We take the wave formula from grade 10, and then this C is a constant which is found on the data sheet provided as the value of C, and then the frequency was also calculated from the previous question, is substituted into the formula, and the wavelength is obtained. So those are the skills which we expect you to be able to demonstrate at the end of this lesson. Now, the baseline activities continue. We also expect you to have an understanding of the intensity of light or intensity of radiation. So we are told in this question that the intensity of incident radiation on the metal is increased. Intensity is increased. Just bear in mind that the intensity is related to the brightness. So when we are told that the intensity is increased, we should know that the brightness of that particular light was increased. So this intensity was increased while maintaining a constant frequency. The frequency remained constant while the intensity was increased. Now, the question says, state and explain what effect this change has on the following. Number one, the effect of intensity on the kinetic energy of the emitted photoelectrons. Number two, the effect of intensity of the effect of intensity on the number of photoelectrons emitted. Now, at the end of this lesson, we will see that intensity has no effect on the kinetic energy of the emitted photoelectrons, and then we will see that intensity has a direct relationship with the number of photoelectrons emitted. So as the intensity increases, the number of photoelectrons is also going to increase. Now let's start with the lesson. At the end of this lesson, we have already seen that you should be able to define the photoelectric effect. You should be able to define the work function. You should be able to define the threshold frequency. So those are the key definitions that you should be able to define at the end of this lesson. You should be able to perform calculations using the photoelectric effect equation, as we have seen on the baseline activity. Then we should be able to define emission and absorption spectra, as we have seen on the terminology that was given. The effect of intensity was seen on the baseline activity, and we should be able to tell that the intensity is related to the number of photoelectrons ejected. Now, the effect of frequency on the photoelectric effect, we should be able to tell at the end of the lesson that the frequency is related to the maximum kinetic energy of the photoelectrons. The lesson objectives continue. We still remind you on the important definitions of this topic. That is the photoelectric effect, which is the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on the surface. Very important. We remind you again of the threshold frequency, which is the minimum frequency of light needed to emit electrons from a certain metal surface. A certain minimum frequency is needed before electrons are ejected from a metal surface, and that frequency is referred to as the threshold frequency. The work function, very important. The minimum energy that an electron in a metal needs to be emitted from a metal surface. So those are the key and very important definitions that one needs to understand and know how to define them for this lesson. And just remember that all definitions should be referred to from the Examination Guideline 2021. Now, the lesson objective continues. We have seen the photoelectric effect equation, and this photoelectric effect equation is repeated here. We want to remind you that the E represents the energy of the photon, which is studied in grade 10. The E is the energy, and then the H is the Planck's constant, which is obtained on the data sheet of your question paper. You are going to see that that value is 6,63 times 10 to the power negative 34. 6,63 times 10 to the power negative 34. There is no need for you to memorize this value, as it is always provided. And then the F represents the frequency. The frequency can be provided for you to calculate the energy. Now, this formula can be altered so that it looks like the second formula here. We use the second formula when wavelength is given instead of frequency. Just bear in mind that H still means the Planck's constant, and the C, that is the speed of light, and the value is also a constant and is obtained on the data sheet. The value of C, you will see on the data sheet, is 3 times 10 to the power 8 meters per second. No need to memorize this value because it is always provided on the data sheet. Now, the work function, WO. WO represents the work function, and this work function can be calculated when frequency is given, and that frequency that must be given must be the threshold frequency. The threshold frequency is given the symbol FO. FO means threshold frequency. If you are given the threshold frequency, you can multiply with the Planck's constant to get the work function. However, you can also be given what is called the threshold wavelength. If you are given the threshold wavelength, you can also calculate the work function by using the formula WO is equal to AC over the wavelength, where H is still the Planck's constant and C is the speed of light, which is given as 3 times 10 to the power 8 meters per second as found on the data sheet. The kinetic energy, which you have studied in grade 10, kinetic energy is half mv squared. Kinetic energy, half mv squared. Now, the mass that we are going to talk about here, this is the mass of the electron. It is also found on the data sheet as 9,11 times 10 to the power negative 31 kilograms. There is no need to memorize this value, as it will be provided on the data sheet at all times to use when calculating the kinetic energy of the photoelectrons. The V in this case is the speed of the photoelectrons as they are emitted from the metal surface, and in this case we focus only on the maximum speed of the photoelectrons as they are emitted from the metal surface. Just a reminder, when electrons are still in the metal surface, we refer to them as electrons. As soon as they are emitted or they are ejected from the metal surface, we now refer to them as the photoelectrons. They are no longer electrons anymore. We refer to them as the photoelectrons. Hence, we are saying this is the speed of the photoelectrons, not the speed of the electrons, the speed of the photoelectrons, because as soon as they are released or ejected from the metal surface, we now refer to them as the photoelectrons. Now, what is the prior knowledge that is needed for this lesson, for you to fully understand this lesson? You will recall that in grade 10, you have studied the electromagnetic spectrum, and within the spectrum, you will remember that there are radio waves, there are microwaves, there's infrared, there is visible light, there is ultraviolet light, X-rays, and gamma rays. And all of these electromagnetic spectrum waves, they differ in terms of their frequency and also in terms of their penetrating ability. Now, you will recall that as we go to the right of this spectrum, we see that the frequency increases. The frequency goes up as we go to the right of the spectrum. And remember that our E is equals to HF. This indicates that the energy is proportional to the frequency. So as the frequency increases, the energy of the electromagnetic waves also increases. The higher the frequency, the higher the energy of the electromagnetic waves. Very important to note that. We continue with the prior knowledge. We want to focus now on the visible light. So this is the visible light. We have seen that before the visible light, we have the infrared. Then after the visible light, we have the ultraviolet. Now let's focus on the visible light. When visible light is passing through a prism, it will be dispersed into a number of colors, which are red, orange, yellow, green, cyan, blue, and violet. And within this spectrum, what we need to understand is that now the frequency increases. The frequency increases. The frequency is increasing as we go down. So we will see red color with the lower frequency compared to orange, and orange with the lower frequency compared to yellow, and violet with the highest frequency within these colors. So violet will have a high frequency, and remember that as the frequency is higher, the energy of the incident light is also going to be higher. The higher the frequency, the higher the energy of the incident radiation. Now, as the frequency increases, we also need to learn also that the wavelength decreases. From the formula, which is the wave formula, we can see that frequency and wavelength, they are inversely proportional. So as the frequency increases, the wavelength decreases. So in the dispersion of light, we want you to be able to tell which light has a greater energy and which one has a lower energy. From this, we see that violet has the greatest energy as compared to all the other colors here. And we see that red has the lowest energy as compared to the other colors. Lower energy, lower frequency. Higher energy, higher frequency. Now, we go back again to the photoelectric effect equation. We remind you again, this is the energy of the photons, this is the work function, and this is the maximum kinetic energy. The formula for calculating energy, if frequency is given, is obtained here. The formula for calculating the energy, if wavelength is given, is found there. The two formulas, they are the same formula. Now, work function, the formula for calculating work function when frequency is given, that is the formula. The formula for calculating work function when wavelength is given, that is the formula there. And then we have the formula for calculating the maximum kinetic energy. Just remember the mass is a constant and its value can be obtained from the data sheet. The value of H is a constant. Its value can be obtained from the data sheet, as well as C is a constant and its value can be obtained from the data sheet. Now, where did it start? Where did this photoelectric effect start? Now, Heinrich Hertz was the first to discover the phenomenon in 1887 when he was investigating radio waves. In 1901, Max Planck showed that energy is quantized. That's where we had the formula E is equals to HF, where H again is the Planck's constant and F is the frequency. Remember that this energy is related to the frequency. The higher the frequency, the higher the energy. The lower the frequency, the lower the energy. Then finally, Albert Einstein explained the photoelectric effect in 1905 by saying that when light shining on a clean metal in a vacuum, we have electrons that are ejected from the metal surface. Just to remind you, these electrons are not called electrons anymore. They are called the photoelectrons. This experiment was done or conducted in a vacuum. Now, let's start now with all the concepts and put them all together. The electromagnetic radiation that we have seen earlier, it consists of small particles or packets of energy. And these packets of energy are called photons. So light consists of small particles or packets of energy which are called photons. So when we refer to photons, we are referring to small packets, small particles or energy packets of light, and those are called photon. Each photon carries the energy that is proportional to its frequency. So this should remind us of the formula E is equals to HF, where we have seen that the energy is proportional to the frequency. Hence, we say each photon carries the energy proportional to its frequency. The higher the frequency, the higher the energy. The lower the frequency, the lower the energy. Now, metals, we have studied in grade 10 that metals have free electrons. And these free electrons are delocalized within the metal, meaning that they are not bound to their atoms. They are free to move. So all metals contain these free electrons. Now, when light is directed into a metal surface, remember light carries photons, carries packets of energy. A photon will collide with one of these free electrons. And when the light or when the photon collides with one of these free electrons, the electron will absorb all the energy that it receives from the photon of incident light. Now, this interaction should only be between a photon and the electron in a one-on-one event, meaning that one photon cannot interact with more than one electron. So this will be a one photon, one electron event, meaning that even if the photon has a larger packet of energy, it can only give that energy to one electron, not more than one electron. Two photons cannot interact with one electron. So it must only be one photon, one electron. The photon can then be reflected without a change in its kinetic energy. So should all the energy not be absorbed by the electron, the photon can be reflected without a change in its kinetic energy, or all its energy is transferred to that electron. In other words, it transfers all its kinetic energy to the electron. So this photon can either be reflected or it can transfer all its energy to one electron. Now, how do we get electrons to be emitted from a metal surface? Now, energy gained is sufficient to the electron to escape from a metal surface if a photon has the amount of energy that is sufficient to release that electron from a metal surface. Then we have the process which is called now the photoelectric effect. If the energy of the photon is not enough to release an electron from a metal surface, then the photoelectric effect will not be observed. The photoelectric effect is only observed when we have light that carries photons that have energy that is enough to release an electron from a metal surface. Now, part of the energy gained by the electron is used to release the electron from the metal surface. And the energy that is left will be used as kinetic energy of the electron. In other words, the energy remaining from the one that is used to release the electron will be used for the movement of the electron. Let's take, for example, we have an electron in a metal. This electron is held to its metal with an amount of energy that is 4 joules. And then we have a photon that is carrying the amount of energy of 2 joules. So if the light that is incident, this is our photon. The photon is carrying 2 joules, and the electron, this is a metal. The electron in a metal is held to the metal with an amount of energy of 4 joules. So in this case, we should learn that the electron will not be emitted. The photoelectric effect will not occur. In the second scenario, let's take the second scenario where our electron is still held together to the metal with an amount of energy of 4 joules. But now the photon comes now with an amount of energy of 4 joules. What we're going to observe is that the electron is going to be emitted from the metal surface, but this electron will not have energy to move away from the metal. Let's take the last one where the electron is still held together to the metal with the amount of energy of 4 joules, but the photon now comes with an amount of energy of 10 joules. In this case, the electron will be emitted from the metal, and this electron will have the difference of the energy of 6 joules. What happened here? 4 joules from the 10 joules was used to release the electron, and 6 joules was the remaining amount of energy that can be used as kinetic energy. So that is what we are trying to say here. Now, this minimum energy, the minimum energy that is required to release an electron from a metal surface, which is the 4 joules in our example, is the work function. So different metals have different amount of work function. So for a particular metal, the minimum energy required to release an electron from a metal surface is called the work function. in our example, this is the 4 joules. The 4 joules is the minimum energy required to release our electron, and in this case, it is our work function. Now, the magnitude of this energy is very small and usually is measured in electron volts. The frequency that corresponds to this energy, remember we're talking about the work function here, and the frequency that corresponds to this energy is called threshold frequency. Remember the formula for the work function is WO is equals to HFO. And remember the frequency is related to the energy. Now, this energy is related to the threshold frequency, which is FO. The relationship is obtained in that formula here. Now, finally, we know that electrons are only emitted if the frequency of radiation is greater than the threshold frequency. Now, the frequency of radiation must be greater than the threshold frequency for electrons to be emitted, or the energy of radiation must be greater than the work function for electrons to be emitted. And if the energy is equal to the work function, the electrons are emitted but do not have the kinetic energy to move from the metal surface.